Everyone, myself Harsh Kumar, student of BSc Chemistry on a second year. This is my video for visually impaired students on topic epoxides. Introduction. Epoxides are cyclic ethers having three-membered rings in which oxygen is one of the atoms. They are also known as alkene oxides or oxyranes. The simplest epoxide is ethylene oxide. In the common name system, epoxides are called as alkaline oxides. In the IUPAC system, they are named as alkene oxides, epoxyalkene, or oxyrenes. The common name and IUPAC names of some epoxides are given below for the sake of illustration. Ethylene oxide, ethene oxide, epoxyethene, oxyrene. 2-butene oxide, 2,3-epoxybutane, 2,3-dimethyl oxyrane. The chemical behavior of epoxides is quite different from cyclic ethers. Synthesis of epoxides. First, epoxidation of alkenes. Epoxides are usually prepared by reaction between an alkene and an organic peroxy acid, also known as per acid, RCOOOH. The reaction is known as epoxidation. Peroxy acids commonly used in this reaction are peroxyfumaric acid, HCOOOH, peroxyacetic acid, CS3COOOH, peroxybenzoic acid, phenyl COOOH, and metachloroperoxybenzoic acid. When a solution of peroxy acid and alkene in ether or chloroform is allowed to stand, epoxide is formed, as illustrated given below. It may be noted that epoxidation of alkenes is a stereospecific reaction in which the stereochemistry of the substituent on the double bond is maintained. Thus, a cis alkene gives a cis epoxide and a trans alkene gives a trans epoxide. The reagent most commonly employed for epoxidation of alkenes these days is magnesium monoperoxyphthalate, MMPP. Its molecular structure is given in the book. Mechanism. The mechanism of epoxidation involves the transfer of an ectophile oxygen atom from epoxy acid to alkene as depicted below. Second, from halohydrins. When halohydrins prepared by reaction of aqueous solution of chlorine or bromine with alkenes are treated with a base, example HX, is illustrated to yield an epoxide. For example, mechanism. The base attacks the halohydrin to abstract the hydrogen from OH part of halohydrin to form an alkoxide ion. The nucleophilic oxygen of the alkoxide ion displaces the halogen from the adjacent carbon to form the epoxide as shown below. It may be seen that the reaction involves intermolecular, that is, within the same molecule, nucleophilic substitution, and is therefore treated as intramolecular Williamson synthesis. It should also be noted that, as in SN2 reactions, the attack of nucleophile takes place from the backside of CX bond. Manufacture of ethylene oxide. Ethylene oxide is manufactured by passing a mixture of ethylene and air under pressure over silver catalyst at 475 to 675 Kelvin. Chemical reactions of epoxides. In contrast to acyclic ethers, which are chemically quite inert, epoxides show high chemical activity. This is due to the highly strained nature of the three-membered ring system. Ring opening reactions of epoxides. In the three-membered ring containing oxygen, the COC bond angle and the CCO bond angle are nearly 60 degrees each. This large distortion from the normal tetrahedral angle of 109.5 degree causes very large strain in the epoxide molecule. As a result, epoxides undergo a number of ring opening reactions quite easily. These reactions take place through the cleavage of one of the carbon-oxygen bonds and may be either catalyzed by acids or brought about by bases or nucleophiles. Acid catalyzed ring opening. Just as simple ether undergo cleavage of the molecule on the reaction with acids, epoxides undergo ring cleavage on treatment with acids even under mild conditions. First, acid catalyst hydrolysis. One of the most important cleavage reactions of epoxide is their hydrolysis to form 1,2-glycols. Hydrolysis takes place even in the presence of dilute mineral acid at room temperature. Second, acid catalyzed reactions with alcohol, for example, as given below. Reactions with halogen acids. Epoxides react with HCl and HBr to form chloro and bromohydrins, for example, as illustrated below. Mechanism of acid catalyzed ring opening. The mechanism of acid catalyzed ring cleavage may be illustrated by considering the hydrolysis of epoxides. In the acid catalyzed hydrolysis of epoxides, the epoxide is initially protonated by the acid. The protonated epoxide then undergoes nucleophilic attack (SN2) by water to cause ring opening by breaking carbon-oxygen bond. The reaction is completed by the loss of a proton as depicted below. Nucleophilic ring opening. Unlike simple ethers, which do not undergo ring cleavage by a base or a nucleophile, cleavage of epoxide ring takes place even by such reagents due to the ring strain in their molecules. For example, when treated with OH ions at high temperature, epoxide rings get cleavage to form 1,2-glycols. Example, ethylene forms ethane 1,2-diol or ethylene glycol. Mechanism of nucleophilic ring opening. The mechanism of nucleophilic ring opening is shown below with the help of basic hydrolysis of ethylene epoxide. The strongly nucleophilic hydroxide ion attacks the epoxide and displaces the oxygen atom from one carbon by SN2 reaction. The product thus formed gets protonated to form the glycol as depicted below. Orientation of ring opening. First, anti-addition. The ring opening of epoxide leads to the formation of products corresponding to anti-addition to carbon-carbon double bond. For example, acid catalyzed hydrolysis of cyclopentene oxide yields trans 1,2-cyclopentene diol. Regioselectivity. Unsymmetrical oxyrenes can undergo ring opening in two different ways and generally lead to different products in acidic and basic media. In acidic medium, the nucleophile generally gets attached to the more substituted carbon, while in basic medium, the nucleophile becomes attached to the less substituted carbon. Explanation. The difference in regroselectivity in acid and base media may be justified as follows. In basic medium, the ring opening is an SN2 displacement by the nucleophile on the unprotonated oxyrene. As in other SN2 reactions, the attack takes place at the less substituted and less sterically hindered carbon. In acid medium, the first step is the protonation of the oxygen of the oxyrene ring. Due to the electron releasing group attached to the more substituted carbon, positively charged oxygen attacks attracts the electron pair of its bond with this carbon to a greater extent than the electron pair of bond with a less substituted carbon. As a result, the more substituted carbon-oxygen bond becomes weaker than the less substituted carbon-oxygen bond. Therefore, ring opening takes place preferably at more substituted carbon-oxygen bond, and the product contains the nucleophile attached to the more substituted carbon. Other nucleophilic ring opening reactions. First, reaction with Grignard reagent and organolithium reagents. Epoxides also undergo nucleophilic ring opening reactions with Grignard reagents and organolithium reagents. The product initially formed on hydrolysis yields a primary alcohol containing larger number of carbon atoms. The epoxide generally used in this reaction is ethylene oxide, and the alcohol form contains 2 carbon atoms more than in the Grignard reagent. Illustrative conceptual questions with answers. Epoxy ethane reacts with ethanol in the presence of an acid but not in the absence. Explain. Answer. Ethanol is a weak nucleophile and such it cannot displace strongly basic alkoxide ions from epoxide. In the presence of acid, the epoxide is usually protonated by the acid. The protonated epoxide easily undergoes SN2 attack by alcohol to cause cleavage of the ring. The reaction occurs as illustrated below. Second, epoxide undergoes ring cleavage at a much faster rate than large-sized cyclic ethers. Why? Answer. As compared to large-sized cyclic ethers, epoxides are much less stable due to large angle strain in their molecule. As such, they undergo ring cleavage more easily and at a faster rate than large-sized cyclic ethers. Then there are some questions for revision. Very short question answer types. What are epoxides? Write the formula, common and IUPAC names of 2 epoxides. Second question. Give one method for synthesis of epoxides. Third. Give one example of intramolecular Wilkinson synthesis. Fourth. Name the reagent commonly employed these days for the epoxidation of alkene. Fifth. How will you convert N-butyl lithium into 1-hexanol? Sixth. Write an equation for the reaction of isobutylene oxide with CH3OH in acidic medium. Seventh. Unlike ethers, epoxides are highly reactive. Give suitable reasons. Eighth. How to synthesize epoxides? Give 2 reactions. Ninth. Give the mechanism of acid-catalyzed ring opening of epoxides. 10th. Differentiate between the acid and the base-catalyzed opening of epoxides. Thank you.